Now, of course, in real life, we cannot get perfectness. So if we get a bit of a few outliers, that kind of strays off that perfect line, then R will drop in magnitude. So the gradient or the orientation of the line doesn't change. But if we have a few outliers, then R will drop somewhere here. So just to show in comparison, if R is somewhere in between 0.6, 0.7, then you may have the presence of quite a strong visual presence of a line, but it's kind of fat, right? Because the points start to stray off that main route, main avenue, and occasionally one or two outliers that are far apart to bring down R. So that will be how the data points will tend to look like. And of course, you can have infinitely many different possible ways to bring down R, right? So oftentimes when we calculate using calculator, Excel, R, or Python, R, the software package, we will get a number, 0.75. Now, you should not immediately jump to conclusion. You should just have a few possible images of the orientation of the points. So what is good is to plot a scatter plot to see the data for yourself before you jump to any conclusion, right? So if it's +1, we know that it's perfectly on a line, but it can also be on many different lines because the gradients can change. So the more the more dispersed the data, the more hairy we get. Although the general orientation is still following the sign of R, right? Like if it is negative 0.6, then it is kind of having a negative gradient, but the points are a bit fatter, hairier, less well-defined. When you reach somewhere near zero, such as plus 0.1, 0.2, minus 0.1, minus 0.2, normally we would expect to see points having random noise. In other words, there's no good sense of a line there. Any line seems possible, any line seems impossible. That's the resulting image that R equals to 0 tells us. However, we also need to be careful, and that's why I'm trying to draw this picture here. Because of the definition of covariance over here, whether sample or population doesn't matter, we know that it is the difference from the mean of X or the mean of Y. If we have numbers, one of the random variable, having the data that is perfectly symmetrical, all right, so if we look at this, if we have a plus area here, and we have another point that's exactly the same distance apart from here, except so the y is the same, but then the x is negative. Then we'll have exactly a negative area to cancel it out, right? Can you see that? If we have a negative area here, then let's imagine either we can have a positive area here or a positive area here to cancel out this area. So if data points are such that they induce a negative area and then immediately they have a symmetrical point that cancels out that area, then we will end up getting a zero correlation. A covariance first and then correlation. So when we end up having that situation, keep in mind that we can have completely symmetrical points. All right, if you have this, or if you have this, they are symmetrical, all right, about the x bar, about the y bar, when it's symmetrical, or both, such as this case. And in the extreme, it can be a circle. Then it will be perfectly symmetrical about both axes. Then you will get R equals to 0. In which case, we conclude that there is no line that is representative. So in this case, it's true. In this case, it's a circle or hexagon or, but there is no good line to represent it. And that's true. In these other two cases where points are kind of linear but symmetrical, unfortunately, then it's a yes and no, right? We can debate and argue that there is this line in between, but R will tell us it's zero. The correlation will be zero. Likewise here, we can say there's a horizontal line, but our R will be zero too. So it's problematic. So there are blind spots like these that we need to be careful about. And one more thing is the case of undefined R. So what happens when we find the correlation of R with a constant number? So when the number doesn't change, when one of the variables, remember R is for X and Y. If one of the random variable is constant, we cannot calculate it, right? For example, when we have a case like this, the numbers are basically here, right? They're lying, they are on a straight line, but it's vertical line. So if it's vertical line, then we are basically saying that all the x values are the same as x bar. So that means our covariance is zero. However, that also means the standard deviation of x is zero. So if we talk about correlation being the covariance divided by standard deviation of x and y, then we have a case of 0 over 0. So in this case, problematic. Likewise, if we have another case, kind of running out of space, oops. If we have another case of the other case where our y values are all y bar. Okay, it's like all the people have the same weight but different heights, or all the people have the same heights but different weights. Then in that case, we cannot really use the calculation here. We have to use the theoretical understanding that covariance with a constant variable is zero, and so because zero will tell us that there is no line, but there is line, except the gradient is infinity, and in this case, gradient is zero. So our line is a vertical line, a horizontal line. So yet our R will be, you know, kind of wrongly reporting that it's zero, or in certain cases, reporting as undefined, because depending on the software, it may be using a zero divided by zero to give you undefined R. So in these cases, one will have to be very extremely careful before we just blindly substitute the data in. So these are the blind spots of the definitions and the formulas. So together as a theory, it works out pretty fine because we know that correlation, covariance, they are meant for two varying variables, right? So we don't purposely want to pretend that we don't know about it, and because in the case where everyone has the same height, it tends to be the case where you actually selectively filter off people who are not of exactly that height, right? Or people of the same weight. Everyone who is of 80 kilograms, then you come in to participate in our experiment. You must have filtered off every other person who is heavier or lighter than 80 kilograms. So these are very artificially generated cases. And then we pretend we don't know, and then we pretend that the weight might vary, and we calculate the correlation. And obviously, we're going to end up, messing up our own conclusions because we knew that this was artificially created. So these cases, one has to be very careful about. In general, however, if we are really exploring data, trying to find out two different measurements, are they related? So for example, if the stock price of a bank rises, does it mean that the stock price of property counter also rises? Well, let's find out the correlation, right? And if it rises and correlation is strong, that means there is a proportionate increase. It may not be 1 to 1, it may be 1 to 0.5. So there may be a small tiny creep upwards, but it's pretty consistent. That is what we want. So a correlation that is very strong, close to +1, means that whenever we observe that the bank counter rises, uh, pretty soon, 1 day, 2 days later, property counter rises. Not much, but pretty consistent. That's good news because you are then willing to kind of place your bet on it, right? Because it's going to be quite a telling, quite an accurate forecast. So that is very important. Yeah. So, and if we discover no correlation, then we may write a program to find some other correlation, right? So that, and certain correlation exists momentarily, just for a fleeting moment. And for that few hours or even few days that you can take advantage of the knowledge of this correlation, you win because then you are able to perform very confident big transactions because you know right at the top of your mind that there's this very strong correlation between the two. We are talking about the what. That means if it goes up, what goes up? Which counter goes up by how much? Right? We're not talking about the why. So oftentimes students may confuse between trying to do science and to do statistics. We are trying to do statistics here. We are not trying to do science here. So the difference is that we answer the what and the how much. And we are not answering the why. This is quite clear, right? We are not there to answer the why. You can of course try to answer the why, but that just means you have to start doing another course. Statistics is portable, right? We can apply this to stock trading. We can apply this to medicine discovery, pandemic study, economics, more because it is talking about the pattern. When we observe this pattern, what happens to the other pattern? And that is statistics. We're not explaining the why, and that is the domain expertise part, the science part, the knowledge and you know, industrial wisdom part. That part you really need experience and in-depth study, right? But even without that, that's the best part. Even without that, you can do statistics, you can do prediction, you can make confident decisions by mastering these uh, properties of descriptives, formulas, and theory that statistics offers.